Okay, in the type 2 stream, okay, so we approximate the convection term as this linear approximation. Okay, and this is our weak form for the Navier-Stokes equations using the stabilized formulation. Okay, and then note, so we typically write this stabilization term as sum over the integrals of all the elements, but just to avoid unnecessary terms, okay, so I am writing this as this continuous integral, okay, but we apply the stabilization at the element level, okay, because like this tau is different for each it could be different for each element. Okay, so this is our convection term now. So here we have un dot del multiplied by un plus 1. So this is an implicit term, okay, but it is not a nonlinear term. So we have the same in the stabilization term. Okay, so this is an implicit term but not a nonlinear term. So what does this mean? So this will contribute to our stiffness matrix. So we will have additional terms to the stiffness matrix. Okay, in order to see what those terms are. Okay, we need to discretize it. Okay, so these are our approximations for velocity and pressure. Okay, so this we have already covered in the Stokes flow. Okay, so we have approximations for u and p, and then w and q. We calculate the derivatives, okay, the gradient and the divergence and so on. Okay, we have covered this already, and we use the same for discretizing this convection term. Okay, so un dot del un plus 1. Okay, first we write this expression in its full form. We expand this using the components. Okay, so un dot, okay, so un, okay, it is a vector, and then this del. Okay, so again, so dou x dou y. Okay, then we apply this to both components. Okay, un x un y. Okay, this is our expression for this convective term. Okay, so un we know. Okay, we can calculate it at this draw point, and un plus 1 we don't know, so we discretize it. And we rewrite this expression, okay, in this fashion. Okay, so we know un and we don't know un plus 1. So as so this needs some practice to see like how to separate this term and rewrite it like this. So what we try to do is we try to separate the known terms and the unknown terms. So un x un y are the known terms, un plus 1 x un plus 1 y are the unknown terms. Okay, so I'm writing this 2 by 1 vector as a product of matrices. Okay, so 2 by 4 4 by 1. This matrix we can calculate based on the previous velocity, and this is the gradient of velocity matrix. Okay, so this is our gradient of velocity matrix. If you add that is why, so here I have this. Okay, so gradient of velocity, we write it as a vector. Okay, so we should do the same convention. Okay, ux by ux, ux by uy, uy by ux, uy by uy. We should not swap them. Okay, if we swap, then we will have some issues. So whatever the convention we use here, we have to use it everywhere else. Okay, so by rewriting this in this fashion, so like this is a matrix C, I'm denoting it as C for convection. Okay, and this is our gradient of u at n plus 1. Okay, we know how to already disguise del u. Okay, so see, we know how to disguise del u. That would be GUU, right? So del u, so GUU. Okay, so this term, okay, so this W transpose we get in like this W transpose and NU transpose, and rho. So un dot del un plus 1, which is c del un plus 1, we get c gu u. Okay, this is the vector of degrees of freedom. This is the gradient matrix. Okay, so for KUU, we get this extra term rho nu transpose c gu, and we can derive similar expression for this stabilization term. Okay, so again we have the same here. This is it. We have already disguised this convection term. Okay, rho c gu u, and this is the gradient of q, and then the stabilization parameter. Okay, so for kpu we get this additional term. If you put them all together, okay, so these are the equations for the element stiffness matrices and force vector. The force vector terms, they don't change. Okay, so we get only additional terms in KUU and KPU. Okay, for KUU this is the additional term, and for KPU this is the additional term. Okay, so this stream converges better than the type 1 stream, but still the convergence deteriorates again, like as we expect it deteriorates for higher Reynolds number flows. Okay, so again the only change we need to make to the stiffness matrix is that inside the stiffness matrix subroutine, so we need to add these two. This is for type 2. When you make changes, so make sure that you don't have the terms for other types of streams. Okay, so first comment the terms for type 1, okay, and then I have the terms for type 2. Okay, these are the only two extra terms. Okay, and I'm going to the main function. In the main function we don't change anything. Okay, and for Reynolds number of 100 I use the same mesh. Okay, I'm going to run it with the type 2 stream now. Okay, as you can see, it is converging better. It is converging better than the type 1 stream. Okay, now the error norm is going below like the tolerance even, right? For 20 time step, it has converged to below the tolerance. Okay, so for type 2 stream, the convergence is definitely better than the type 1 streams. Okay, and what happens if we increase the Reynolds number 2000? Of course, it would struggle, but we expect it to be better than type 1 stream. The type 1 stream couldn't even handle it, diverged right from the beginning. But here, so we don't see the divergence, it is still going fine. Okay, and after our 10 load steps, remember, so we are increasing the load in the first 10 load steps. So after 11th load steps, is again, as you can see, the error is reducing slowly. Because it is a high Reynolds number flow, the convergence would be slower. So it is not monotonic decreasing, it is increasing, decreasing, so it is oscillating. In order to get better convergence, we have to reduce the time step size, and that means we need to run for longer time. So okay, so by at the end of 30 load steps, so it reached an error norm of 1.79 per minus 2. So that means it has a converged as per our wish, our tolerance. Okay, so this is the final matrix form for the type 2 stream with the type 2 approximation for the convection term. Okay, so here this is an implicit term with the convective velocity evaluated from the previous time step. Okay, so this is better than type 1 stream, but still not good enough. So because like we still have to reduce the time step and then run it for longer, like spend more time. Okay, so before I go on presenting a better stream, so there is a type 3 stream, remember. So in the type 3 stream, so we calculate the convective velocity as an extrapolation from the previous two velocities. Okay, so this is the only difference that we need to make. Okay, sorry. Okay, so before going to this, so this calculation of the C matrix. Okay, in the gross point loop, once we calculate velocity x and velocity y, so we can prepare the C matrix. Okay, so using this expression. Okay, so I forgot that, so going back to that. Okay, see, and then we can add the, like we calculate this those two extra terms. Okay, for this formulation, type 2 formulation. In the type 3 stream, it is very similar. Instead of un, here we have 2 un minus 1. Okay, so here as well. So that means the only change we see is in the C, the convection matrix. Okay, so here instead of un, we have again 2 unx minus un minus 1x. Okay, so and so on. Okay, so like implement this on your own, but this stream still struggles to converge. Again, in my experience, for study flow problems, there is not significant difference between type 1 and type 2 stream. In some cases, even type 2 stream oscillates much higher. Okay, so it oscillates much higher, like more severely when compared to type 1 stream. So there is not a significant difference for study flow problems, but we do have some advantages for unstudy flows. But that's a story for another day. Okay, so this is for type 2 and this is about type 2 and type 3 streams. So you can check the slides, you can check the expressions and also the code and see like how the implementation is done and run the cases for different Reynolds numbers and with fewer, like smaller time step size and so on.